Can everyone see my screen, right?
Yeah, we can see it.
Okay, perfect. So today I'm going to talk about the best research practice with MONAI, and yeah, let's dive into it. So just few sentences to introduce medical image analysis. It just means to gain the high-level understanding from the images. The application could be disease diagnosis, treatment planning, and surgical guidance. And we use it for several purposes, like precise radiotherapy, or like even recently we applied for the COVID screening. Okay, next one. So as you can see, there's a lot of like different image modalities inside of medical image domain, like CT, MRI, ultrasound. An application could be various, with segmentation, classification, detection, survival model prediction, and even the natural language processing. So the goal of this analysis process is to combine the clinical expertise together with the artificial intelligence, or more recently, we're trying to combine with deep learning or machine learning. So I made a figure about this year's MICAI's keywords. Basically, I put all the titles of the MICAI paper this year into a word cloud. I try to plot the statistics of the words from the titles. As you can see, there are three keywords are quite significantly used by a lot of papers, which means it will be the most interest to most users. So first one, segmentation. If I remember correctly, last year's half the paper are related to segmentation applications. And the second word is deep. So now a lot of work, a lot of papers, a lot of authors were trying to apply deep neural networks in their application. And so the word is learning. So learning not just deep learning, but it also could be like machine learning, classical machine learning techniques. So this keyword will interest the most audience in MICAI. So I think we can get it a step further to have a case study for the 3D medical image segmentation. So in one sentence, 3D medical image segmentation just to take 3D medical images and input and extract 3D structures of organs and tumors. As you can see from the figure left and right, the left figure shows the segmentation overlaid with a CT image, a segmentation of liver and the spleen. The right-hand side is a 3D rendering of a segmentation result of the chest vessels and also the COVID lesion. And since we have a lot of applications, our algorithms, so for the model training, we always ask questions like, what is the optimal deep learning solution in medical imaging? You can see the pipeline could contains a lot of meat, data. You have label and image. You need to do the data processing. So one part is pre-processing, how you're gonna normalize data, how you're gonna do the resampling, and also how you do the data augmentation. Then you need to choose various neural networks from the big pool in the public domain. And then once you've done this processing and the network selection, then you also need to decide what will be the hyperparameter you're going to use. That's also the tricky part. So you can see just it's not like a one-click solution. It has a combination of all of the components. So the challenge for those kind of large-scale medical image segmentation could be various. It could be because it covers a lot of the clinical applications. For example, different anatomical objects in different image modalities. And it is hard to collect large-scale pixel-level annotation. Normally, it takes hours or days to accomplish multi-organ annotation in the whole body CT. And also, as I said, it's a 3D medical image segmentation. It takes a large chunk of GPU memory during model training and inference. Because of the medical image, normally it's a 3D or even a 4D, which has a large, will take large GPU RAM. But do we have a solution Yeah, I think currently we can see yes, we have a solid solution so far to really resolve the issues. Back to the case study, we show the case of a 3D spleen segmentation. So let's say we have abdominal CT from the public domain, which is medical segmentation decathlon. In total, they have like 41 CT volumes available for training. We partition them for 32 and 9. 32 of them using for training, and 9 of them used for validation. So currently, across different data set or leaderboard, the state-of-the-art performance of the spleen segmentation is around the die score like 95%. But so far, normally like the publicity available implementation normally will take several hours to train the segmentation to reach such performance. Here, I mean like using like a single GPU. But here, now, we can achieve it within 1 minute using a simple UNet on one single GPU. Okay, let's dive into the solution. So as I said, like the solution is contains multiple components. You have the data loader, like a reader. You need to do the pre-processing. Sometimes we want to cache those like intermediate result from the after the data loading to the GPU RAM to speed up training. And for model training, we have to choose loss function optimizers, learning rate, etc. And also for the validation, because medical image has various size of themselves. So we want to carry out sliding window inference. And for the sliding window inference, we also want to conduct on the GPU. Then eventually we reach its final model. First thing, I want to talk about pre-processing and augmentation. So pre-processing in medical image is quite critical because so pixels or voxels inside of medical image has its own physical meanings. Let's see, it has spacing or orientation or fine matrix. So it defines the physical size of each pixel and voxel and its orientation. You can see this is like one example of the transform list that we have for the spleen segmentation task. It covers pre-processing and also the augmentation. You can see the key component here is listed on the left part, like a spacing D. Spacing D here is trying to resample the whatever input image towards the target resolution or target spacing. You can see here in the setting, we're trying to resample it towards like 1.5, 1.5, 2.0 millimeter versus spacing. So why we do that? We want to try to simplify the application for the segmentation model and make the model like easier to learn. And also like we do the same thing for the orientation. We are trying, because like in a lot of occasions, like scanner are scanned from a different starting point with different orientation. We are trying to use this orientation D transform to align all the image in the training pool toward the same origin and with the same orientation. So again, it's also used to simplify the task. The next one is the scale intensity range. Basically, for the CT image, its intensity basically means it's a half field unit. It has its own like physical meanings. So which means for tissues, for bone, for chest, or for air, it has own like intensity range. So for like specific object, like spleen, it's a soft tissue. So we want to choose the soft tissue window. Let the model focus on learn the intensity within this window to achieve a better performance. And after all those three like pre-processing steps, we want to train the model. So, but as again, after resampling, the image size could be varies a lot. So we want to here we use the random cropping based on the foreground and background labels. So first, it can handle various image sizes, and also it can balance the training samples, which means like you can because you want the model see some crops like ROIs patches with foreground region and some patches without foreground region, like a purely background regions, to kind of make the model training to be balanced. And the next thing I want to bring it up is automated mixed precision. It's invented by another team within NVIDIA. So basically, you're gonna speed up training by converting part of operation, model training operation from full precision to half precision. And those half precision operation will be run at tensor core of your GPU. So this figure shows the comparison with or without AMP. So for the two experiments, we fixed the random state, so which means basically the training behavior of two different trials will be very similar. As you can see, if we use epoch as x-axis, you can see the training curve of the training loss curve with or without AMP are very similar, very identical. But if we, on the right hand side, if we switch the x-axis to total training time, you can see the similar curve of the AMP with AMP will be squeezed by half, which means with AMP can further reduce the training time by half. That's quite impressive speed up we gain with AMP. And also you can, from the left figure, you can see the training loss curve are almost identical. So we think this performance is really reasonable. And also, we further narrow down the well, where's the improvement from. So we decouple this training process into several components. Let's see the forward operation and backward operation, and the continuous loss function, and then it's like optimization. You can see, given different training patch size, the most benefit using AMP is from forward and backward operation. You can see the most gain you got from those like two columns, and with large batch size, you can see the gain or improvement even better. So with AMP, you almost have like more than two times like improvement during the training. That will largely improve your training efficiency. And also, another benefit of AMP is it will reduce the training memory consumption. As again, compared to example, if you can see this is a memory consumption during training. So during different setting of a patch size, you can see the memory consumption with AMP is always lower than the one without AMP. And if the input patch size grows larger and larger, the memory reduction rate will become like larger and larger. Yeah, that will somehow like eases the burden of the GPU memory consumption with larger medical images. And the next thing is called a NovaGrad. NovaGrad is kind of another new technique we have another NVIDIA team has brought up for model training. Basically, is trying to have a layer-wise adaptive segment momentum to the optimizer, and it will speed up training very, very significantly. So we do have the implementation in MONAI. I encourage the users to give a try to your application. Normally, based on our observation, we feel it's like the convergence rate is quite impressive, even with the same setting with other optimizers like Adam or SGD. And next thing is like a loss function. So for segmentation, now like a dice loss is quite popular choice for users because like cross entropy is only focused on the pixel-wise accuracy, but dice loss will give you like a better constraint on the global structure of the object. And the dice loss basically is like is 1 minus the dice score. So 1 minus dice score is like I assume most of the users here understand know what dice score is. Like basically it's overlap divided by the sum of the two, like foreground, foreground and ground truth region and predicted regions. And so this is like a very popular loss. So what if we want to make a like step further to combine this dice loss with cross entropy loss together? As I said, dice loss is mainly for global constraint for the structures, and cross entropy is for like penalize the pixel-wise loss functions. So which means you have the global structure together with a local, like say the boundary area constraints, then eventually you will have the better performance. So we made a very interesting experiment. So we made a one-line change. So for the loss function, from the dice loss to dice cross entropy loss, just we change the one line and to make a comparison to see the learning curves. And also we enabled 2 other additional terms. We made like a square prediction, which means like X or Y here, basically you make a square here. And then for batch, so we turn it a batch true because like in the small batch of the model training, the medical image we have with the batch size normally small, so we compute the dice score over entire batch instead of for each instance. So that will be further improve your convergence rate. The comparison is quite interesting. So we do the experiment with and without NMP. So you can see the original, it's like the original solution we have, and it's the right curve shows with AMP turn on. You can see this is a validation accuracy curve. With or without AMP, the training will be very gradually get improved from time to time, but it will like take a while to be activated. But if we simply make that line changes, you can see the improvement quite significantly. The model get activated right away, and you will after it get activated right away, and it maintains the high level all the time. So this is online. This is only one line change. We kind of like keep the same for the rest configuration. You can see this loss function could play a huge roles in your model training. And also there's other implementation improvement. I guess like yesterday, Nick, one of our colleagues, Nick, has given a presentation about it. It's like now we have the fully GPU-based data caching. Just cache the intermediate data or original data into GPU-based data pre-processing, augmentation, and also a fully like GPU-based sliding window. That will be. And also GPU-based sliding window inference is much better than the CPU-based or like partially GPU-based. And the entire process in this pipeline, there's almost no CPU operation involved. Only like after fourth epoch, when all the data cache into the GPU RAM, and no CPU operation gonna be participating into the computation. So now, if we make a further comparison about the time to reach expected accuracy, as I said, like 95% using MONAI or newest version, you can see the improvement is quite significant. So this is the old solution we have in ClaraTrain. ClaraTrain basically is like is another product from NVIDIA. It's like kind of it provides models and the training configurations for different segmentation applications. So the old solution we had in ClaraTrain is going to take around 20 minutes to reach certain like this dice score. But now with our improved solution, now it only takes 54 seconds. And even if we switch the V100 GPU to A100, the computation will be even faster. Now to reach 95% die score, it will take only 40 seconds. Yeah, and for this findings solution, we have I just said we made it like available online into the tutorial. So let me click it on. It's now fully available on project MONAI GitHub. It's under tutorial acceleration, a fast model training guide. It has a lot of contents. Firstly, how to show you how to use a profiler to profile, to find out where's the bottleneck in your pipeline, to find out which part is like slow, very slow, which one you can further improve. And there show different usage of different libraries. And next, yeah, even there's one NVML can show it's like this library of NVIDIA SMI, and you can plot your GPU utilization rate. And some technique I just mentioned, the GPU-based operation, algorithm improvement, and yeah, it's a lot of things. And multi-GPU training, multi-node training. And also we added three, actually we have three applications, spring segmentation, spring city segmentation. This is what I just said. Another, the brain tumor segmentation, basically it's like a BRATS. It's data from BRATS challenge. And yeah, we can also improve very significant improvement over the training efficiency. Yeah, you can see now from a few hours just to like a few minutes, quite impressive. And also we have another example for the pathology applications. I would encourage you guys to look into this documentation. We did spend a lot of time on this, but the result is quite encouraging. Let's get back to talk. And also for the, as I said, like the cloud training is a 4.0. So although it's not fully open source product, but you see we provide like a lot of model and their configurations in the configuration. And also the configuration for those like applications is fully leverage the components in MONAI, which means like a transform, loss function optimizer, everything you can find you directly use the MONAI transform optimizer loss function. So even you know for your own application, you can use those like examples as a reference and directly call your MONAI transforms to train your own model. Yeah. Yeah. Now I want to talk a little bit about the advanced topic. So one of the achievements made from our team is like this paper we're calling it's like a searching for optimal neural architecture for 3D medical image segmentation. So we are kind of trying to do this kind of differentiable neural architecture search for the medical imaging. It's published in CVPR this year as an oral presentation. The goal is trying to search within this kind of searching space is the input and the right top as output, trying to search the optimal architecture from this searching space. It's densely connected searching space. The algorithm need to decide whether to connect different feature maps. You can see whether we should connect different node here or should we connect node here. Or for the numbers on the edges, you can see connecting edges, which does indicate different operations. So 0 here, for example, 0 means skip connection, and 1, 2, 3, 4 means different version of the convolution. Then in total, after like this kind of differentiable searching process, you will reach the architecture like this. And we validate this approach algorithm on this public data available data set. It's a public challenge called Medical Segmentation Decathlon, MSD. It is a public challenge with 10 different tasks of like a 3D medical image segmentation. It covers both CT and MRI, and it covers organs and tumors, lesions, and even vessels. Yeah. So the outcome of the algorithm is quite encouraging. So now is like the current DINS approach as the #1 entry on this leaderboard. So which means our searching algorithm, it is general, and it could be apply for multiple application with really good performance. And also the original implementation is part of, it's like a, it's based in MONAI. So currently it's a work in progress for future release. Yeah, for maybe hopefully for the next release of MONAI. Okay, what's more? What more can MONAI or even like we can offer from the within or with or inside or outside NVIDIA teams? First thing, under the research contribution repo, there's a work called LAMP, large deep net with automated model parallel for image segmentation. In some occasions, the image size could be very large. You cannot even fit one, or model size could be very large. You cannot even fit one like ROIs into the model training. So there's a way to do the automatic model parallelism, which means if you have multiple GPU, you can partition your like feature map at the same layer across different GPUs. Then you can fit into the large image or like image patches into the model training, to gain good performance. And also, if you want to do the inference for like for inference for the large image patch without sliding window, then you can. But if the image is size too large, you can consider this approach to further decouple this feature maps across different GPUs in parallel and do the inference. That will be another alternative of sliding window inference. Another work is called Uniter. This is invented by another one of our colleague. He's trying to leverage the capacity of transformer-based encoders to segmentation model, and you can see that from the figure, it's quite a very interesting work, and it had very promising result on the PDCV public challenge, and that's a challenge for multi-organ segmentation. Yeah, it's also available on the research contribution repo. You can take a look, and yeah, the very quite promising steps we get so far. And the next thing is like federal learning. So we also have an example for federal learning with MONAI. So our team, another team, invented this library called NVFlyer to enable federal learning inside for internal and external people of NVIDIA. So so the MONAI can be combined with that library and do federal learning on your side. Okay, that will be my presentation. There's quite a lot of content. I'll be happy to answer all of the questions from all of you. Thank you.
Yeah, that was great, Dong. There's a few questions in here. Some people asked for the paper. I did link the paper in Discord. And then people were asking for your slides as well. So I will post the slides as I can get them onto the GitHub repo, so people can go look at them later.
Right.
And then someone just asked also, MONAI 0.7, when is that going to be released? I think yesterday we had release candidate 5 for 0.7. So hopefully either maybe early next week, I think is maybe when we're targeting for release. For 0.7. It'll be soon at least. And then either later this week or early next week is when you'll see MONAI 0.7 released.
Yeah.
But let's see, questions for you. It was I see 3 different questions here. Richard already kind of answered one of them, but someone was asking for the sliding window inference method, is it still beneficial if they have access to large memory GPUs?
Oh, that's a good question. So it depends. So let's see, if it depends on the model and the patch size you select for training. For example, if you use only like a small patch size for model training, and you want to do the inference on the entire large patch for inference, or like the whole image as the inference, normally it won't give you like a good performance. So the sliding window will be better. But if you train the model with a large patch size, image patch size, and definitely you use the whole image like as it to do the inference will be better, because sliding window sometimes will have some like small, very subtle artifacts on the boundary. So with using the entire image as a for inference, that will be for the improve that issue.
Yeah. Okay, great. So there's two more here. So someone asked, was CE loss attempted for the 3D spleen segmentation runs in addition to dice and dice loss?
Sorry, can you repeat the question?
Was CE loss attempted for the 3D spleen segmentation runs in addition to dice and dice losses? So they're asking about the loss functions that were tested for the 3D spleen segmentation run. And was anything else tested aside from dice and dice?
Oh yeah, CE loss is tested, but CE loss has much worse, like at least the convergence rate comparing to other like even dice or dice CE loss. It could take a longer time to get converged. And also we tested another loss called dice focal loss. That's dice loss combining with focal loss. That one is also like quite promising. It also has it shows also faster convergence for the model convergence for the model training. So that's a good alternative if you like for your application.
Yeah. Great. So we have one more, and then we'll move over to the next presentation. So the last question here is, someone asked, have you looked into how large the impact of training time with only changing of the window? For example, was changing the windowing itself super impactful outside of other experimental designs, since a lot of other non-soft tissue input data was suppressed? They're just trying to generally understand how the HU and intensity, whether it's impacting or not, because in Nifty, they said from Nifty, and how it kind of is impactful on that process.
So for the window, the intensity window and the patch size, right?
Yeah.
So for intensity window, I think I feel like it is necessary to do this kind of windowing for specific regions, like a specific object. Let's say the for bone or for soft tissue, if you select the right window, then your model training will very efficient. And for the patch size, it's a good question. It really depends on the object you are trying to learn, because sometimes like for small objects like a lesion or like tumor, it's better to train with a smaller image patch. Training with a smaller image patch will make the model sensitive, which means you get a higher chance to identify the tumors from within the image. But for organs, for bones, it's better to have a large image patch size, because segmentation, those objects, it may require a lot more like global context. So if you like a larger image patch, definitely give you like a more global context to help you make a better segmentation result.
Great. Thanks, Dong. So we're going to move over to our next presentation. And Dong, hopefully you stick around for a little bit and you can answer any questions that come up in chat as well. So I think there might be another one in Discord, but yeah, thank you.
You're welcome.